Continuing on here with our discussion of entropy, let's talk about what happens when a solution forms. We kind of talked about this in the second chapter of this class as well, but we're going to talk more about it now. So when a solution forms, there's actually two different things that are happening. There's two different effects, I guess you could say, on the entropy of the system. So the first one is that you have a solid, so that would be this stuff down here, that is in a very crystalline state. So in this particular example, we are dissolving sodium chloride in water. So we have sodium ions and chloride ions that are going to dissolve into the water and leave this very ordered, very crystalline state. That is going to be a big increase in the entropy because it's going from very, very ordered, very, very compact, not spread out at all, to going into solution, much less ordered, very disordered, very random placement of the ions throughout the mixture. So that is going to be an increase in the entropy when these ions leave the crystal lattice and go out into solution. However, that's not the only thing that's happening. Because if you notice here, the water, if it's not near an ion, is just kind of floating around doing its own thing. That is a higher order of entropy than the water that is right here, directly around those ions. What happens when something dissolves in water is what develops are called spheres of hydration. And we're actually only showing one sphere of hydration here, but depending on the ion, you can actually have multiple spheres of hydration. So you have water molecules that are not bonded to the ion, but they're held fairly closely just from the attraction of the very polar water molecules to the charge on that ion. So they're held nearby, and that is less entropy than if they were just floating around doing their own thing. They are more ordered, being held close to those ions than they would be otherwise. And so we actually have two opposite effects occurring here, where we have the increase in entropy because we have a solid going into the aqueous phase, but then we have a decrease in entropy because the water that was just randomly moving around before, some of it is now held around these ions, and that is a decrease in the entropy. And so this is going to be kind of a fight between these two properties as to which one wins out in the end, which one is going to have the greater effect. Now, usually, I hesitate to put an exact number on it, but if I was just going to guess, I would say probably 90+% of the time. I wouldn't go up to 95% probably, but there are the vast majority of the time, the solid dissolving into solution is going to win out. That is going to be a larger change in the entropy, and so for the vast majority of cases, and for our purposes, we're just going to assume all of them because we're interested in the general trend, not the exception to the rule. For our purposes, we are going to assume that when we have something that dissolves into water, that is going to increase the entropy. But just so you are aware, there are some situations where you actually have a decrease in entropy when you take an ionic compound and it goes into water. I believe the only situations where that happens are the same situations where, if you remember from the solutions chapter, there were, if you remember the graph, we had, I believe it was temperature on the y-axis, and then on this axis it was the solubility, I believe. So how much would dissolve, and for most things the graph looks something like this, where there's maybe differences in the slope, but for most things, as the temperature increased, the solubility increased. But there were one or two, and I think in that graph there was only one, that actually decreased with as the temperature increased, the solubility decreased. And so I believe that these situations here where the solubility was decreasing as the temperature was increasing. Those situations were when we had actually more entropy in the system. If we dissolved, if we dissolved it, we had less entropy because there was a very, very strong interaction between the water and the ions that were released into solution. A few other things, and we've actually already talked about some of these already, but a few other things that in general will increase the entropy. So when gases are formed from liquids or solids, either through evaporation or through reactions taking place, that is going to increase the entropy, because again, gases have more entropy than liquids or solids. If we have liquids or solids that are formed from solids, again, same kind of thing, either by reactions taking place or by just melting, that is going to be an increase in entropy. The number of moles of gas increasing, that would be most likely from a chemical reaction occurring, but I guess you could technically just have someone just put some more gas into the sample. That would increase the amount of entropy. And just in general, the number of moles increasing is going to increase the number or the amount of entropy. So if we take a look at this example here, we're asked to predict the sign of delta S, the change in entropy, for each of these processes. So I want you to go ahead and pause the video, take a look at each of these three situations, and try to decide if we're going to have an increase in entropy, which would be positive delta S, or a decrease in entropy. So pause the video now. All right, so in part A here, we have gaseous water, steam, going to liquid water. That is going to a lower, so to speak, phase, a lower energy phase. And so delta S for this process would be negative. We'll have less entropy at the end because gases have higher entropy than liquids, and so we're going from a high entropy to a lower entropy, and so we're going to have a negative delta S. Part B, we have solid carbon dioxide subliming. If you remember what sublimation is, that is going directly from the solid phase to the gas phase. That is going to be a very large increase in the entropy, because gases by far have the most entropy, solids have the least by far, and so we're going to have a big increase in entropy for part B. Part C, it's a little bit tougher to tell, because everything that's involved here is a gas. But if you notice, we have 2 moles of gas on the left and 3 moles of gas on the right. So because we have 3 moles of gas on the right, delta S is positive. We have more moles and more moles of gas on the right than left, so we are going to a higher entropy system, and so delta S is positive. We have another example here. So we have the combustion of propane happening. And so we're given the equation there as well as the enthalpy value for that reaction. Part A asks us to calculate the entropy change in the surroundings associated with this reaction if it happens at 25 degrees C. Part B is going to ask us to find the sign of the entropy change for the system. Notice here, surroundings, system. And then part C, determine the sign of the entropy change for the universe. Will this happen spontaneously? So go ahead and pause the video, and we will work out each of these things together after that, after you give it a shot. All right, so part A. We're asked to find delta S for the surroundings, the entropy change for the surroundings. And if that sounds familiar, it's because a few slides back here, we have this handy little equation. So the change in the entropy of the surroundings is equal to negative delta H for the system divided by the temperature. And so we are given delta H for our system. It is negative 2044 kilojoules. Don't forget, though, that that equation is negative delta H for the system. And again, we're assuming here that our system is the reaction. We kind of have to make that assumption because we're not given any information about anything else, so it kind of has to be our system. So negative the delta H for our system divided by the temperature, which does need to be in Kelvin. It needs to be in Kelvin. Anything involving entropy needs to be in Kelvin. 25 degrees C is 298 Kelvin. Just adding 273 to that number. And so if I do that math real quick here, the two negatives are just going to cancel each other out. And so we're going to have 2044 divided by 298. And that is going to be 6.86 kilojoules per Kelvin. And those are the normal units for entropy, either kilojoules or joules, either one, per Kelvin. That is the normal unit for entropy. All right, so that is the answer for part A. Oops. Let's try that again. Okay, so part B, it asks us to find the sign of the entropy change for the system. So we found the entropy change for the surroundings. So if the entropy change for the surroundings is 6.86, it's tempting to think, oh, that must mean that the entropy change for the system is just going to be the opposite. And sometimes that is the case, but we can't just take this value and take the opposite of that and say that's the entropy change for the system. Sometimes that'll work, sometimes it doesn't. Instead, what we're going to do is we're going to do something very similar to what we did in the last one, because we're not actually asked to find the value for the entropy change. We're just asked to find the sign. Is it positive or negative? And so we're just going to take a look at the reaction. Everything involved in the reaction is a gas, so we don't have any clues in terms of liquids versus solids versus gases, because everything is a gas. But if you notice here, we have 6 moles of gas on the reactant side, and we have 7 moles of gas on the product side. So simply because of that, we can say that the sign for the entropy change of our system is going to be positive. So this is one of those cases where the surroundings, it has a positive increase in the entropy, and so does the system. We can't just say, kind of like what we did with enthalpy. Usually with enthalpy, if we knew that the only things that were exchanging energy were the system and the surroundings, there was nothing else happening, we could just say whatever the system lost, the surroundings must have gained. Doesn't quite work like that with entropy. Entropy is a little bit of a different beast. So they actually both have an increase in entropy in this case. So that leaves us here with C, determining the sign of the entropy change for the universe, which should be pretty straightforward here, because again, we're not asked to find the actual value, we're just asked to find the sign. And given that the entropy change of the universe is just the entropy change of the system plus the entropy change of the surroundings, and given that both of these ended up being positive, we know that the entropy change of the universe must also be positive. All right. I think we'll call it here for this video. Have a nice short one. When we pick up in the next one, we're going to talk about Gibbs free energy and how that will help us determine if reactions are spontaneous or not.